Right, June 2022, paper 2, question 18. And I haven't read the question yet. Right, an object O of mass m kilograms. So, as always, label your diagram, label what you know. So, O of mass m kilograms. So, coming down here, we've got a force mg, mass times gravity. It's hanging from a ceiling by two light inelastic strings of different lengths. So, the lights, we can ignore the weight of them. Inelastic, we can assume they're not stretchy. So, the tension in this one will be acting that way. Should we call it TA? And the tension in this one will be acting up that string because they're trying to stop that bit at O from falling down. Okay, the shorter strength of length, 0.8 metres, is fixed to the ceiling at A. The longer strength of length, 1.2 metres, is fixed to the ceiling at B. And we have a height here. Now, this is screaming something to do with a triangle to me. Anyway, so I'm going to draw a triangle. Okay, and we know that this length here is that length there is 0.8 and the other length over there is 1.2. That length there is 1.2 and that perpendicular height there is 0.6. Okay, right. I know what we're going to have to work out. Right, okay. Show that the tension in the string is, in the shorter string, is over 30% longer. Right, okay. So these strings, because they're acting that way and that way, they've got a vertical and a horizontal component, haven't they? Right, so the measurements are here because we need to work out the angles, basically. That's what they're there for. So if we split that into two right-angled triangles here, that one will be 0.6. This one here will be a hypotenuse at 0.8. And I want this angle here. So I'm going to use, what have we got here? We've got opposite, adjacent, hypotenuse. So cos of theta is equal to the adjacent over the hypotenuse. Inverse cos of 0.6 divided by 0.8 equals 41.4. It doesn't say not to do it in degrees, so I'm going to do it in degrees. Or actually 0.6 divided by 0.8 gives us 3/4. Actually, we might need to leave that as 3/4. Well, we'll see. We'll keep it like that. Okay, and we can also call this angle here. If we draw another right angle triangle for the other side, that side's 0.6, that side's 1.2, and I'm after this angle here that I'm going to call alpha. So cos of alpha is 0.6 over 1.2, which is a half, which gives us an angle of cos alpha is a half, that's 60 degrees. Right, okay. Okay, show that the tension in the string, blah, blah, blah. Right, okay, so let's resolve vertically first of all. Because is it moving? No, it's just hanging. It's hanging, it's not moving. So that means what's going left is equal to what's going right, and what's going up is equal to what's coming down. So left and right, the only horizontal forces we've got are... Oh, excuse me. Oh, I'm going to sneeze. Right. That's there, that's theta. So the horizontal bit of this force going that way, if that's theta there, then that will be opposite. We want this bit opposite that. So TA sine theta, that's your... must be equal to TB sine alpha. Okay, so if we do the sine of theta, which was 41.4, we get 0.6613. You know what? I'm just going to do the cheeky little trick with right angles here. If cos of theta is 3/4, That means 16.5. This is root 5. Okay, so sine theta. Because I want to keep my answers accurate, I'm just going to do it this way. So sine theta is root 5 over 4. Is that right? No, it's root 7, isn't it? I can't add up. Root 7 over 4. There we go. Right, okay, and equally we can do a cheeky triangle over here. We've got if that's alpha, that's 1, that's 2. So that will be root 3. So sine of alpha is root 3 over 2. Right. Sine over root 3. Yeah, no, that. Right, okay, yeah. Right, okay, so we've got TA. So root 7. Oh, come on, Louise. Write the right thing down. You can tell it's the holidays. So root 7 over 4 times TA is equal to root 3 over 2 times TB. I want to show the tension in the shorter string, that's TA, right? Therefore, TA is equal to root 3 over 2 times TB divided by root 7 over 4. So if on your calculator you do root 3 over 2 divided by root 7 over root 7 over 4, you get 1.31 basically TB when we round it. So TA is equal to 1.31 TB, therefore TA is approximately 31% more than TB. As required. Now you didn't need to do all that cheeky Pythagoras stuff here for that. You could have got values out of your calculator and just calculated them, but I just wanted to be as accurate as possible. Right, now we know that the tension in the longer string is known to be 2G. Find the value of M. Right, okie dokie. So the tension in the longer string, so that's TB, is 2G. Right, so I'm going to replace with, no I'm not, I'm going to replace that with 2G. 2G. So TA is equal to 2.62G. Right. Okay, and then the only thing left to do is to resolve vertically. Okay, so vertically, going up, you've got TA cos theta plus TB cos alpha. Remember, if we're going vertically, we want this bit here. And because we've measured these angles here, we've gone cosy to them. So we want the cos of them. And that's got to be equal to what comes down, which is mg. Okay. Now we know that TB is 2G, so I should have put that in instead of being silly like I am. So 2G. Let's go down a little bit. From earlier, we know that cos theta is 3 over 4, so 3TA over 4 plus 2G times our cos alpha, which was a half, equals mg. Okay. TA, we know is 2.62G from earlier. So we've got 3 times 2.62 divided by 4 equals 1.965G plus, now that cancels down to just a G, is equal to mg. So altogether we've got 2.965. G equals mg. Therefore, M equals 2.965 kilograms. Now, I think that due to rounding, I think that should actually be 3. But maybe due to rounding somewhere along the lines. Probably where we did this 2.62 here. If we'd have left that accurate, I think we'll probably get that G was equal to 3. Okay, so if the mark scheme says G is equal, M is equal to 3, I think that's probably why. Right. Okie dokie. Hope that helps.